Good morning, everyone. My name is Wilson. I'm from Cape Verde, Africa. I guess the only African here presenting a paper. My work talk about efficiency of fire safety system based on a fire dynamic simulator, FDS. It's like our research since 2015. So we are working on it. I hope you guys can enjoy my presentation. It was a model applied to a data center. Okay. As an introduction, I will present two images showing an event of fire in a data center, where we can see in the left a fire happened in a data center in South Korea, and another one in cowboy miners in Thailand. Okay, it both happened in 2014. Fire in data centers is normally occurred due to the high temperatures from the machinery. So we have to take. It's so important to have to study the temperature in the place, and to examine the predictions of pressure, and we have to take measurements to prevent those events. This is our physical model. Up you can see the real picture, and below you can see the model that we designed. It's a building that is structured in two parts. We have like an L shape, call it NOC, because it's Network Operating Center, and then another one that we apply our study, that is the cube. Okay, inside the cube we have two rooms. One we call main room, and another one the safe room, where was applied our study. For the simulation scenario, we try to model designing our model like using the existing fire system there based on IG-55. It was hard work trying to model the IG-55 extinction gas. Hell of work, actually. So to extract the result, we designed and placed some devices. Here we can see the device's name and the label. Here we show and we change the supply to a nozzle to the supply, because we couldn't put inside the model lumped species. So we changed the nozzles to supply surface, so we can insert inside our model the IG-55 gas. Here you can see the device mapping top view, where it's placed all the fire. You can see in the UPS the fire source, and where is placed all the devices that we use. Also, you can see a device mapping on the side view, where we can see the height of all the devices and how far from the fire it is. Okay. For this simulation scenario, we also consider a pressure system, where we base it on a poster that Thunderhead Engineering did in November 2014, where we ask about how to model pressure relief vents in the discussion group. So they did a post, explain how to do it, and it works fine in our model. Thank you, Thunderhead. So we did a grid sensitive analysis, that a small test where we compare results between 5 type of cell dimensions, where we use intentional 2 tests with 0.12 meters, where we are going to present some unexpected, unpredictable results on the performance of the computer. here we show why we use two cell dimensions with the same cell dimension, where we vary the cell divisions. In the axis, we can see here some difference in the axis values of these tests. We can see here some the results of the temperature at 30 seconds of simulation. We can compare the results between the 0.16 and 0.08 meters, where we can see it's almost the same result. How do you say that in English? I'm kind of losing the word right now, but it's kind of we have a similarity of results between 0.16 and 0.08. Here we compare the results between all the tests, and we could see that the CPU ranging about 9.8% to 100%. Talking about the random access memory, where it ranges about 12% and 17%. But what surprised us is the runtime of our simulation, where we could see here the 0.12 meters that we use the same value, and we could see like 3 hours of difference between the same cell dimensions. It was like an unpredictable result. We didn't expect this value, so we were like trying to use and to do more grid sensitive analysis in this model to improve our work. So it is a small test, so we just present this like an image to summarize our grid sensitive analysis, where we show which one is the optimal solution found, comparing the mesh resolution and the computational effort. We could see that the cell dimension of 0.16 meters show with the optimal solution, because it is the best, you have the best mesh resolution and the best computational effort if we compare the results between the 0.16 and the 0.08 meters. So to present our final model summary is like doing what is the parameters that we use to model to design our model. We must note that all the parameters we use will influence the results. So everything we did here has to be reviewed from other study and future studies we will do we will do in the future. So regarding to the temperature, we can compare it here that thermocouple 1 registered lower temperature than the others, but a question that can pop in your mind is why, if it is closest to the fire, but it is closest to the fire, but in the lower area, it can be justified by one of the principles of thermodynamics that we call convention, where in the upper areas we have a higher temperature, and the lower areas we have lower temperatures. So we could see here that the thermocouple 3, that is the farthest thermocouple from the fire, and it is in the upper area. So here we present the heat detector's results, where it ranges about 21.15 Celsius degrees and 24 Celsius degree. If we walk into the data center with a thermostat in the doors of all servers, we will get the same result that we get in this model. So analyzing the spread of smoke, we could see here a smoke in the time of 10 seconds, where it is getting to the ceiling. These results can be compare it to the activation of our gas, that we can see in the time that it activates in between 10 seconds and 15 seconds. If we compare it to the activation of the gas that is due to the, accordingly to the smoke detector, we could see that the gas was activated between 10 seconds and 15 seconds. It shows some consistent results in our model. So we could see here, we can see here the model and the injection of our particles. It is showing the IG55 gas inside our model. And we can see here the heat release rate, that it remains almost constant during the simulation, and from 28 seconds until the end, we could see it tends to decrease. But we couldn't increase the time because we had some numerical instability. We put the question in the discussion group, but it is a problem that we are facing now, and we couldn't solve it since 2 years of our investigation and research. So we are working on it, and we hope in the next conference we'll bring the results of the solution that we solve. Regarding to the local pressure, theoretically it was expected an increase of pressure because we inject some particles inside the building. So why we didn't have upper and an increase of pressure? It due because in the data center they have a lot of airflow. So in the front of all servers we have a fan. In the back of the servers we have an exhaust. So it creates an air flow. So we couldn't have the reading of an increase of temperatures. So to clarify this, to explain to the managers of the data center what we do and what we did was we turn off and disable all the servers, all the fans and the exhaust, so we could stop the airflow, so we could get some increase of pressure where we see that the pressure relief vents works fine when it gets to 270 pascals. So we could see the pressure there. We could see there that the pressure relief vent is doing its job, like relieving the pressure inside the building. So to better understand, we put some vector slices where we could see how the velocity of the air is spreading and how and where it is going. As a conclusion, we can say that our model works helping the decision making of the managers in some security cases while we are talking about fire situation, and likewise we want to say that the results of grid sensitive analysis have to be more research, so we could enhance the performance in the future simulations, save the running time, and trying to get better and better results. This is some references in my paper. You can see more of these references. And as future works, we are working on a model that is based on a pathfinder, and we are comparing it to EVAC module from FDS that allows to analyze the building structure for evacuation case. So what we are doing here is trying to show the people in our country that we have some solutions, because in our country they just seek for solutions when bad thing happens. So they don't seek for solution to prevent for this thing to happen. So it is what it is. So sometimes we can get fire and people can be dead. So what we are trying to do is showing people that FDS and Pyrocene Pathfinder is working as a model that can prevent those events. So we can talk about it later if you want, if you are interested. Yeah, it is. Thank you. Yeah.
Thank you, Wilson. Do we have any questions, comments?
I would like to say that if you are talking too fast, to be more slowly, because I don't get too fast conversation, okay? Yep.
In your model, did you consider airflow or gas flow through the servers? And if so, how did you model that?
What we did was we modeled an obstruction, and in the front of every obstruction we put a surface that like a fan, and at the back we put some exhaust. And in the front, the air is like put inside the space, and the back, what it does is exhaust the hot air from the machinery. In my paper, it is more explaining how I did it, so you can read a bit of it. If not, we can see my model later on my computer. You can understand it. Yep.
Other questions, comments? No? Gerald.
Yeah, I saw this very low pressure as a result. Did you check the number of pressure iterations in your simulation?
The pressure, what?
There's in the out file of FDS, you get a number of pressure iterations, which is by default set to 10. And after 10 iterations, by default, it stops the pressure iteration. But if you have a situation where you need more, then you get an error in the model if you don't check this.
Yeah, I think like if we had more increase of pressure, you mean, or?
Yeah, in situations where you have overpressure devices or some special situations, you can need more iterations to find a convergent solution, the correct solution for the pressure. And if you don't verify this detail in the output, maybe you get an error in the pressure. Just a remark.
Okay.
Other comments in the back?
Thank you. Yeah. Couldn't understand what is the question, but.
In your model, when you're injecting the agent, you were injecting it as droplets that are evaporating. That's correct?
What? I didn't understand.
When you're injecting the IG55, you were injecting it as liquid droplets that then evaporate. That was how you were injecting the agent?
Yeah, we are injecting it like a lumped species, but it is like when it goes into the floor, it just disappears. I don't know how. I don't know if it gets inside the exhaust or what, but.
Okay, so we're injecting particles?
Yeah.
Yeah. So if you're injecting particles that are evaporating at very low temperatures, as a person who wrote the evaporation model in FDS, you have to be very careful to make sure that the properties you specify for the gas and the properties you specify for the liquid are consistent, right? Because FDS is going to conserve the enthalpy of the liquid when it evaporates it into a gas. And if you define inconsistent properties, that can result in instabilities, because FDS is going to do, right, what you put as the inputs, and if those inputs are non-physical, a non-physical result can lead to an instability. So you have to make sure that the enthalpy of the liquid phase, the enthalpy of the gas phase are consistent with the heat of vaporization that you're defining. Otherwise, you're likely to get an instability.
Why your voice are fading? I don't know why. It's like. Yeah, but I get your question, I get your comment. Is like there is a lot of work yet to do in my model. So we wanted to do some real tests, but real simulation in a data center is a lot of money. It's so expensive. In our country, they don't, put the money for the researchers or for investigation. So we have to, how do you say that? In Portuguese, I know, but in English, we have to seek for a solution and to travel out of the country just to try to prove them that they could be wrong if they don't do a real test and trying to prevent the fire. You understood or not?
Any other comments, questions? All right. Thank you very much again.
Okay, thank you guys.